the solar system is a mere speck in comparison to the vast galaxies and clusters of stars. Within a 100 light-year radius, there are thousands of other stars. Some are barely visible against the blackness of space, while others are so bright that they can even be seen from other galaxies. There are also many invisible objects in space, ranging from brown dwarfs that are roughly the size of Jupiter to rocky exoplanets. Some may be home to life, while others could pose a danger. The size of our galaxy dwarfs all this diversity. Across its vast expanse, there are at least 200 billion stars. This vast array of unique space objects is impossible to explore in its entirety. We will now discuss some of the nearest ones. According to galactic standards, the area on the outer edge of the solar system is sparsely populated with stars and other objects. Yet, it is known that approximately 50 stellar systems can be found within a 15 light-year radius of Earth. The total number of stars is 65. Some are single stars, while others have two or more components. The formation of celestial bodies is still ongoing in many of these systems. We will need to map the surroundings in order to analyze this vast variety. We will travel dozens of light years through space as we venture beyond our planet. Now is the time to reach for the stars. After traveling 6 light years from the Sun, we will arrive at our first destination. A small red dwarf with the designation GJ 699. This star is also known as Barnard's star. It's remarkable for its speed and for being able to cross the disk of the Moon in 180 years. Its great speed and proximity to us are not the only reasons for this. Barnard's star is approaching the solar system at a speed slightly above 100 km/s and will become our nearest star in approximately 10,000 years. The distance between Barnard's star and the Sun will be only 3.8 light-years by then. The red dwarf, however, is so dim it won't be visible from such a distance without assistance. It will only be visible through optical equipment. Its radius is 6 times smaller than that of our Sun, while its mass is only 17% of that of the Sun. Barnard's star is very cool, like all red dwarfs. Its surface temperature is just 3,134 K, or just under 2,860 degrees Celsius. It's not surprising, then, that the star has a luminosity 2,300 times less than our parent star. In 2018, the results from a 20-year study of the proper motion of stars were published. This could provide evidence of the presence of an exoplanet near Barnard's star. Calculations show that it is a cold super-Earth with a mass not less than 3.2 times that of Earth. The planet GJ 699b is located 0.4 AU away from the center of the system. It takes 233 days to complete its full orbit around the parent star. The exoplanet's orbit does not pass between Earth and the parent star. Therefore, it is difficult to perform a spectral study of the object. Even so, mathematical models can give us some insight into its characteristics. Barnard's star, which is dim compared to the Sun, delivers to the exoplanet only half the energy that Earth receives from the Sun. The temperature of the surface is a mere 105 K, or minus 168 degrees Celsius. It is possible that radioactive decay or tidal disruptions have released enough energy from the planet's core to create a warm subsurface ocean. Barnard's star is one of the oldest known stars. Estimates suggest that its age is over 10 billion years. This is only a small fraction of the life expectancy of a red dwarf star. Barnard's star is a high-priority object for an interstellar mission because it is close by and moving in the right direction. On the other side of our Sun, we find the exact opposite of the dim red dwarf. Sirius is the brightest star in the night sky, and it's 8.6 light-years away from Earth. The star, which appears as a single source of light from Earth, is actually a binary star system. The two components are at their maximum separation, which is about 30 AU. The main star is also known as Sirius A. It's a bright blue and white star that has a mass 2 times greater than the Sun. It is also about 70% bigger in diameter than the Sun, and its surface temperature can reach 10,000 K. Sirius A emits up to 25 times the energy of our Sun. The bright Sirius A makes its companion, Sirius B, almost invisible in the background. This white dwarf has a diameter of about 6,000 kilometers and a mass that is very similar to the Sun. Its surface temperature, like that of all stars of its type, is extremely high, reaching 25,000 K. However, this white dwarf is not 1,000 times brighter than its companion star. It is actually much dimmer due to its size. Sirius has not yet had any exoplanets detected through long-term research. This may be due to the relatively young age of the stellar system, as well as the unique position of the plane of the ecliptic. The transit method cannot detect hypothetical exoplanets because they do not pass between the star and Earth. One hypothesis states that Sirius B's stellar fuel supply was exhausted approximately 120 million years ago, and it transformed into a red giant. It shed its outer layer and became a compact, very hot white dwarf. The protoplanetary disk of gas and dust that surrounds the young star system is a direct result. This explosion destroyed any planets that were present at that time. The remnants of the explosion scattered in space, denying any forming planets a chance to survive. Both components of the system move around a common center of mass in orbits that are moderately elongated and complete one cycle every 50 years. Sirius will slowly approach Earth over the next 60,000 years, becoming brighter and more visible at night. After reaching a distance of 7.5 light-years, the system will begin to drift slowly away from us. Sirius A and its companion will share the same fate after approximately 150 billion more years. A massive flare can temporarily boost the brightness of a star by thousands of times, but within months the star will completely fade, disappearing from the sky. Sirius is permeated with intense ultraviolet radiation and stellar wind. We will make a maneuver to approach a smaller star that is 14 light-years away from Earth. The name of this star is Wolf 1061. The star is actually a red dwarf, with a diameter of around 30% that of the Sun. Its surface temperature is 272 K, which is approximately 3,000 degrees Celsius. Wolf 1061, like all objects of its class, is dim. Its luminosity, which is 0.14% of the Sun's, means that the star cannot be seen with the naked eye. However, this red dwarf has one of the most diverse and abundant planetary systems among nearby stars. 3 exoplanets, all rocky and similar to Earth in composition, have been found in its immediate vicinity. The conditions on each celestial body are still very different. Wolf 1061b is the name of the first and nearest exoplanet. It is located 0.038 AU away from the center of the star system. A full orbit takes about 5 days to complete. The object has a mass between 1.5 to 2 times that of Earth, with a radius 20% larger than our planet. This celestial body is likely tidally locked, facing its star on one side all the time. The star is so close that flares and the stellar wind from the star are almost certain to have stripped away any atmosphere. These factors render the exoplanet unsuitable for the genesis and sustenance of life. Wolf 1061c is located at a distance of 0.089 AU from its star. It completes an orbit around the star roughly every 18 days. It is therefore within the habitable zone of the star and can be considered a potentially habitable celestial object. Wolf 1061c is approximately 3.4 times more massive than Earth and belongs to a class of super-Earths. Its radius is 1.6 times that of Earth. While the surface gravity is 60% higher than we are used to, its equilibrium temperature is lower because it receives less energy from the star than Earth does. It is 223 K, or 50 degrees C below 0 degrees, slightly higher than Mars. However, due to variations in temperature throughout the day and seasonally, it is possible that liquid water exists on the surface of this celestial body. This probability increases with a dense atmosphere and a greenhouse effect. The planet's conditions could be approaching those of a habitable world. Wolf 1061c is the fifth closest of all potentially habitable exoplanets. The third object is Wolf 1061d. Its orbit is noticeably elongated, and the distance between the parent star and the planet at aphelion is 0.73 AU. Perihelion is located 0.21 AU from the center of the system. This celestial object takes 217 Earth days to complete one full orbit. It is estimated that the mass of Wolf 1061d is roughly 7.7 times that of Earth. If it turns out that this celestial object is rocky, its radius should be about 1.7 times that of Earth. However, if this planet falls into the category of mini-Neptunes, with a thick, multi-layered atmosphere, then its diameter should be at least 2.2 times greater than that of Earth. Wolf 1061d, despite its relatively high orbital eccentricity, never enters the habitable zone of its star. It is unlikely that this celestial body would be able to support life. But it could still hold great scientific value in terms of planetary evolution. The system is a top priority for future exploration. It is very likely that new discoveries will be made soon. The star Wolf 1061 is notable for its position at the edge of what is called the local interstellar cloud. This is an area of space that contains hot but highly rarefied hydrogen. The temperature is about 7,000 K, and there are only 0.3 atoms per cubic centimeter. The Milky Way's average is only about half of this value. For about 10,000 years, the solar system has been moving through the local interstellar cloud. Our system is situated at the edge of this cloud, which has an average diameter of 30 light-years. Alpha Centauri, for instance, is already located in the so-called G cloud. In contrast, we will spend another 2,000 or so years in our cloud before we enter a thinner and even hotter region. The local interstellar cloud was formed when two giant bubbles of hot cosmic gas collided. It also has a magnetic field and a radiation field. Despite its high energy, the cloud is not a threat to Earth's organisms. The solar wind provides a reliable shield against cosmic hydrogen, and Earth's dense atmosphere absorbs the majority of particles that manage to penetrate the heliosphere. In spite of this protection, Antarctic ice has been found to contain traces of iron-60, also known as interstellar iron. The local interstellar cloud is believed to be the only place from which it could have originated. As we continue to explore space, we have discovered an unusual star that has captivated our attention for a number of reasons. AP Columbi is located 27.4 light-years away from Earth. It is a star that has fascinated astronomers. It is striking to learn that this star was born around the time when the dinosaurs went extinct on Earth. It is also remarkable that the star was born in a location 450 light-years away from where it is now. Young stars usually remain close to their stellar nursery for a very long time, often for several 100 million years. Upon examining the movement of AP Columbi, it becomes evident that it was likely part of the cluster IC 2391. This cluster consists of about 30 stars that are bound together by their common origin and direction of movement. A few million years ago, one of these stars exploded, disrupting the delicate balance of a number of cosmic bodies, and AP Columbi was propelled out of its home by this catastrophe. This star is a very small red dwarf with a mass of only 13% that of the Sun. However, it emits 4 times as much energy as any other celestial object with the same parameters. Its radius is also twice as large as what would be calculated using modern stellar structure theories. These mysteries have been addressed by analyzing the star's composition through spectral analysis. AP Columbi contains an unusually high amount of lithium. This element is normally found in large quantities in protostellar clusters, but quickly depletes following a thermonuclear reaction. This suggests that AP Columbi is still very young and not yet in its main sequence phase. As a result, AP Columbi is volatile and unstable, prone to violent explosions and ejections of stellar material. During these events, its brightness may increase up to 10-fold for a brief period. Such events can strip away the atmosphere of nearby exoplanets and bombard their surfaces with ultraviolet radiation. Observations show that no large celestial objects are within 4.5 AU of this star, and it is likely too young to have formed a fully developed planet. Nonetheless, AP Columbi is a unique object in the universe and is crucial for understanding the early stages of stellar evolution. We've seen that not all stars have planetary systems. Our next stop will be near the orange dwarf Gliese 370, located 37 light-years away from Earth. A single exoplanet, Gliese 370b, was discovered in 2011. The object has a mass between 3 and 4 times that of Earth and was discovered using the radial velocity method. According to current knowledge regarding the formation of celestial objects, this newly discovered world is likely a rocky planet with a diameter about 30% greater than Earth's. Under such conditions, its gravity must be at least 40% higher than that of Earth. Gliese 370b is located 0.26 AU away from its parent star and completes an orbit around it in 54.4 Earth days. The exoplanet is situated within the habitable zone of its star. If the albedo of its surface is similar to Earth's, the average temperature should be around 25 degrees Celsius, which is a few degrees warmer than Earth's. Exoplanets located at a greater distance from their parent stars may not be tidally locked and can have a separate day-night cycle. This also contributes to a more even distribution of heat across the surface of the celestial body, potentially resulting in a milder climate. The moderately high gravity should flatten the planet's surface, which, combined with an abundance of liquid water, could give rise to large, shallow, and warm seas. These environments are considered to be highly conducive for the emergence and sustenance of life. At the time of its discovery, Gliese 370b was considered one of the most promising exoplanets in terms of potential for hosting biological life. However, recent research suggests that conditions on its surface may be less hospitable than originally thought. The atmosphere of this celestial body may be dense enough to create a strong greenhouse effect. Even if the more pessimistic predictions are correct, the average surface temperature of the planet is likely no higher than 78 degrees Celsius. This corresponds to an approximate temperature range between 30 and 100 degrees Celsius, similar to the climate of Earth during the Archean period. Gliese 370b remains a promising exoplanet in the search for extraterrestrial life, and it is imperative that exploration of this intriguing world continues. We have traveled over 50 light-years from our solar system, Within this radius, there are more than 1,000 single stars, the majority of which are bright. There are also binary stars and even groups of stars. Castor is the most impressive example, with its complex and astounding 6-component system. This stellar system, located 50 light-years away from Earth, is visible to the naked eye. Castor is the second brightest object in the Gemini constellation, and the 23rd brightest object in the night sky in general. Humans have known about it since ancient times. The system is complex because it contains 6 components. Castor A and B are the 2 brightest stars in the system. They resemble Sirius but are bluish-white in color. Each of these stars has a companion red dwarf nearby. The binary pairs take 445 years to complete an orbit around each other, with a separation of approximately 110 AU between their centers of mass. About 600 AU away from Castor A and B, there is another compact binary system, Castor C, consisting of 2 nearly identical red dwarfs. Each of these has a mass about 0.6 times that of the Sun and a surface temperature of around 3,900 K. These 2 stars are so close to each other that they complete an orbit in less than 20 hours. The entire Castor system orbits around a common center of mass in a roughly circular orbit with an orbital period of 14,000 years. As of now, Castor has not been confirmed to have any exoplanets, but if they exist, they will most likely be found at the outer edges of the system. Astronomers have detected changes in the orbital period of Castor C, which implies that there could be a brown dwarf nearby with a mass about 49 times that of Jupiter. Calculations indicate that it is 14 AU away from the Castor C system and completes an orbit around it every 54 years. Like many other red dwarfs, Castor C might have rocky exoplanets nearby. In such a scenario, the sky would be a spectacular sight. 2 red stars would be seen circling each other continuously in the sky. On the opposite side of the sky, a pair of stars, each 100 times brighter than Earth's moon, would cast an eternal twilight. At this stage, it is not possible to confirm whether this scenario is accurate. The stars that we have observed are distant from each other, but they all belong to a structure spanning around 300 light-years, known as the local bubble. The local bubble contains thousands of stars, as well as several large structures, including the local interstellar cloud. The local bubble was formed by successive supernova explosions that occurred between 10 and 15 million years ago. It is a vast cloud of interstellar gases that have been heated to temperatures around 1,000,000 Kelvin. Due to its high temperature, the gas within the local bubble is expanding, resulting in a density that is about 10 times lower than the average density in the galaxy. The hot ionized hydrogen within the bubble continuously emits X-rays. Fortunately, the Earth's magnetic fields and atmosphere, as well as the Sun's magnetic field, protect us from this harmful radiation. There are other similar formations surrounding the local bubble. One such formation, which I believe you meant to refer to as Bubble 1, but please double-check the name for accuracy, is an example of a bubble created by a supernova explosion in the vicinity of Antares. This formation has been interacting with our local bubble for an extended period. This interaction has resulted in the formation of large, dense structures near the boundary of the local bubble. The solar system will reach the edges of the local bubble in a few million years.